Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Augustin-Louis Cauchy's 1821 publication, The Cours d'analyse de l'école polytechnique, with its first part titled Analyse Algebraic, represents a foundational moment in the history of mathematical thought, while the lectures it documents originated in the years leading up to its printing, including the period around 1818. The work itself stands as a definitive declaration of a new philosophy for calculus and analysis. It sought to replace the intuitive, often physically or geometrically motivated, reasoning of the 18th century with a program of uncompromising algebraic rigor. This essay will undertake a direct evaluation of the work's internal claims, proceeding through its key conceptual stages to assess the construction of its logical edifice. We will examine the specific definitions, the substance of the proofs, and the coherence of the argument Cauchy presents, thereby tracing the establishment of a paradigm that would define modern analysis, complete with its towering strengths and its profoundly instructive imperfections. Section 1. The preliminary discourse as a methodological manifesto. The work commences with its preliminary discourse, which functions as a clear statement of intent and a powerful critique of antecedent mathematical practice. Cauchy's central claim in this introduction is that analysis has lacked the rigor universally admired in geometry. He attributes this deficiency to a reliance on arguments drawn from what he terms the generality of algebra. This was a prevailing 18th century belief that algebraic identities holding for real numbers could be assumed to hold for complex quantities, infinite series, and other extended domains, often without specific justification. Cauchy explicitly repudiates this approach. His argument posits that for analysis to achieve demonstrable certainty, its propositions must be derived from a small number of core principles through a chain of incontestable logic. He proposes to establish analysis upon the concepts of variable quantities, limits, and functions, treated in a purely algebraic and arithmetic fashion. Evaluating this claim requires recognizing its revolutionary character. Cauchy is proposing a complete reconstruction of the foundations of calculus. The evidence he offers is primarily rhetorical at this stage, an appeal to the ideal of logical purity. The success or failure of his argument is therefore contingent upon the execution of this program in the subsequent chapters. The discourse effectively serves as a promissory note, a contract with the reader that the remainder of the text will deliver a system of analysis whose conclusions flow with deductive necessity from clearly articulated first principles. It is a bold and unequivocal rejection of the formalist, manipulative style of his predecessors, including the great Lagrange, whose work on the theory of analytic functions had attempted a similar algebraic foundation but through the problematic use of infinite Taylor series as primary definitions. Cauchy's claim is that his method, grounded in the concept of the limit, provides a superior and genuinely secure alternative. Section 2. The foundational trinity of function, limit, and continuity. In the initial chapters, particularly the first and second, Cauchy lays the very cornerstone of his analytical structure by providing explicit definitions for function, limit, and continuity. He defines a function as a relationship where, for a variable quantity, there corresponds one or several determined values. This is a broad and general conception. Following this, he presents his celebrated verbal definition of a limit. He states that when the successive values attributed to a variable approach a fixed value so as to end by differing from it by as little as one desires, this fixed value is called the limit of all the others. The critical claim here is that this definition is sufficient to banish the metaphysically fraught concept of the infinitesimal as a mysterious, non-zero quantity smaller than any assignable number. Instead, he introduces infinitesimals as variables whose limit is zero. This is a masterful conceptual move, transforming a static ontological problem into a dynamic, Process-oriented definition. His definition of continuity follows directly from the concept of a limit. A function of a variable is continuous between two given bounds if, for each value of the variable between those bounds, the numerical value of the difference between the function at the variable plus an infinitesimal increment and the function at the variable itself decreases indefinitely with the value of the increment. In essence, an infinitesimal change in the input produces an infinitesimal change in the output. The evaluation of these definitions reveals their immense power. They successfully provide a language for discussing analytical concepts without recourse to geometric diagrams or appeals to motion, fulfilling the promise of the preliminary discourse. However, their methodology relies heavily on the intuitive understanding of phrases like as little as one desires and approach indefinitely. The definitions are verbal and dynamic, lacking the static, quantified precision of the later epsilon-delta formalism developed by Weierstrass. Cauchy's framework operates on a conception of numerical quantity that presumes the properties now formalized within the structure of the real number continuum, yet he never creates an explicit theory of the real numbers themselves. His claims are therefore built upon an unstated and unanalyzed foundation, a fact that represents a subtle but significant logical gap in his program of absolute rigor. Section 3. The intermediate value theorem and the assumption of completeness. A pivotal moment in the Kerr's de-analyze is the proof of what is now known as the intermediate value theorem, presented in the notes following Chapter 5. The theorem claims that a continuous function which takes on values both above and below a certain number must also take on that number itself at some point in the interval. For the special case of finding a root, if a function f of x is continuous between x equals and x equals b, and if the function of a and the function of b have opposite signs, then there exists a value of x between a and b for which the function of x equals 0. Cauchy's proof is a landmark of the new method. He rejects prior arguments that relied on the geometric evidence of crossing an axis. His method is purely analytic and algorithmic. He begins with the interval from a to b, divides it in half, and selects the subinterval at whose endpoints the function continues to have opposite signs. He repeats this process of bisection indefinitely, generating a sequence of nested intervals whose lengths approach 0. He then argues that the sequence of left endpoint and the sequence of right endpoints must converge to a common limit. Because the function is continuous, the function's value at this limit point must be the limit of the function's values at the sequence of endpoints. By the construction, this limit must be 0. The evaluation of this proof reveals both the genius of the method and its most profound unstated assumption. The algorithmic procedure is brilliant and constructive. The claim that this method proves the theorem, however, rests entirely on the existence of the limit point of the sequence of endpoints. Cauchy's argument implicitly assumes that any increasing sequence of numbers that is bounded above must converge to a limit. This is a fundamental property of the real numbers, often called the axiom of completeness or the least upper bound property. Cauchy provides no proof for this principle. He treats it as self-evident. His proof of the intermediate value theorem is therefore incomplete by the very standards of rigor he champions. It demonstrates that if a limit exists, then it must be a root. It fails to demonstrate that the limit must exist within his system. This lacuna highlights the critical dependence of his entire analytic program on an intuitive, yet unformalized, understanding of the number. Section 4. A rigorous framework for infinite series. Chapter 6 of the Kerr's de-analyze provides a systematic and rigorous treatment of infinite series, representing one of the work's most immediate and influential successes. For much of the 18th century, mathematicians manipulated infinite series with extraordinary skill but with an alarming lack of concern for their convergence. Divergent series were frequently used in derivations, leading to both brilliant insights and outright paradoxes. Cauchy's primary claim in this chapter is that an infinite series has a meaningful sum only when it is convergent. He provides the first fully articulated definition of convergence. A series converges if and only if the sequence of its partial sums approaches a finite limit. This single definition transformed the field. It established a clear criterion for distinguishing meaningful series from formal and potentially nonsensical expressions. Building upon this foundation, Cauchy proceeds to develop a toolkit of practical convergence tests. He introduces the comparison test, the ratio test, and the root test. The ratio test. He demonstrates that if the absolute value of the ratio of successive terms in a series approaches a limit that is less than 1, the series converges. For the root test, he shows convergence if the nth root of the absolute value of the nth term approaches a limit less than 1. The evaluation of these claims shows them to be entirely sound and flawlessly derived from his definition of a limit. They are powerful, general-purpose tools that allow for the determination of convergence without needing to know the value of the limit itself. This section of the book is a triumphant vindication of his methodological program. By applying his precise definitions of limit and convergence, he brings order to a chaotic area of mathematics, providing the working analyst with a set of reliable instruments. The coherence and utility of these tests provided powerful evidence for the superiority of his approach over the generality of algebra, which had offered no such systematic way to ensure the validity of its infinite processes. Section 5. The celebrated error concerning the sum of continuous functions. Within the very same chapter that achieves such success with series of constants, Cauchy makes one of the most famous and instructive errors in the history of analysis. He presents a theorem which claims that a convergent series of continuous functions is itself a continuous function. Specifically, if one has a series where each term is a function of a variable x, and each of these functions is continuous, and if the series converges for all values of x in a given interval, then the sum function of the series is also continuous in that interval. His proof proceeds by arguing that the remainder of the series, the sum of the terms from a certain index n onwards, can be made arbitrarily small by choosing a sufficiently large n. Then, for this fixed n, the finite sum of the initial n terms, being a sum of continuous functions, is itself continuous. Therefore, a small change in the variable x will produce only a small change in this initial sum. The combined change in the total sum, he argues, can thus be made as small as one wishes. The evaluation of this proof reveals a subtle and fatal flaw in its logic. The argument requires a delicate exchange in the order of two limiting processes. One process is making the remainder small by taking n to infinity, the other is making the change in the function small by taking the increment of the variable to 0. Cauchy's proof tacitly assumes that the speed at which the remainder approaches 0 is independent of the value of the variable x. This is a much stronger condition than simple convergence at each point. The Norwegian mathematician Niels Henrik Abel, in a 1826 paper, identified this very lacuna. He constructed a counterexample, a convergent series of sine functions, which are all continuous, yet whose some function possesses a discontinuity. The flaw in Cauchy's theorem lies in its failure to distinguish between pointwise convergence and what would later be termed uniform convergence. The theorem is true only under the stronger, unstated condition of uniformity. This error is of immense historical and intellectual importance. It demonstrates a limitation of Cauchy's intuitive understanding of limits when applied to the more complex setting of functions. It shows that even in the hands of its creator, the new rigor had its boundaries, and that the behaviour of infinite collections of functions held subtleties that his initial framework was unprepared to capture. The refinement of his theorem would become a major impetus for the work of later analysts like Seidel, Stokes, and ultimately Weierstrass, who formalized the concept of uniform convergence to correct the claim. Section 6. Algebraic legitimization of complex quantities. Later chapters of the Cours d'analyse, particularly chapters 7 and 8, extend the algebraic program into the domain of so-called imaginary or complex numbers. At the time, these quantities, involving the square root of -1, were widely used as a powerful computational device but lacked a secure theoretical foundation. They were often viewed with suspicion as formal artifacts whose philosophical status was ambiguous. Cauchy's central claim in this part of his work is that these expressions can be treated as legitimate algebraic objects, subject to the same rules of arithmetic as real quantities, without needing a direct geometric interpretation. He defines a complex number as a symbolic expression of the form a plus b times the square root of -1, where and b are real quantities. He then meticulously demonstrates how the standard operations of addition, subtraction, multiplication, and division can be defined for these expressions in a way that is consistent and free from contradiction. He further defines a function of a complex variable and explores the conditions for its continuity, directly paralleling his treatment of real functions. Evaluating this section reveals a key aspect of Cauchy's methodology. He effectively sidesteps the ontological debate about whether imaginary numbers exist by treating them as formal, symbolic constructs. Their legitimacy derives from the internal consistency of the algebraic system he builds with them. This approach was profoundly effective. It provided a working foundation that allowed him and others to begin developing the rich and powerful theory of complex analysis, while the geometric interpretation of complex numbers as points in a plane, developed by Wessel and Argon, would ultimately provide a more intuitive picture. Cauchy's purely algebraic approach was crucial for integrating them into his program of rigor. It demonstrated that his method, based on formal definitions and logical deduction, was not confined to the real variable but could be extended to create new and coherent mathematical worlds. His claims in these chapters are sound as framework successfully establishes the algebraic groundwork for what would become one of his most significant areas of research. In conclusion, a direct evaluation of the claims within Cauchy's Kurzgesagt reveals a work of profound and complex achievement. Its overarching ambition, to ground analysis in a new standard of algebraic rigor based on the concept of the limit, was largely realized. The definitions of limit, continuity, and convergence, though verbal, provided a powerful and coherent framework that successfully brought order to the theory of infinite series and established a new, abstract language for calculus. His algorithmic proof of the intermediate value theorem was a tour de force of this new method. Yet, the evaluation also uncovers the system's critical vulnerabilities. The entire structure rested upon an intuitive and unanalyzed conception of the number continuum, a fact exposed by the implicit assumption of completeness in his most famous proof. Furthermore, the celebrated error in his theorem on the sum of continuous functions demonstrated that the subtleties of infinite processes involving functions required a conceptual tool, uniform convergence, that his framework had yet to forge. The Kurzgesagt is therefore monumental not only for the logical edifice it successfully constructed but also for the precise location of its structural weaknesses. These very lacunae became the precise points of departure for the next generation of mathematicians, who, by addressing the questions Cauchy's work left unanswered, would complete the arithmetization of analysis. The work's enduring significance lies in its powerful, if imperfect, execution of a new vision from mathematics, one where intuitive evidence was supplanted by deductive proof and whose internal arguments, in both their successes and failures, set the agenda for mathematical analysis for the century to come.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.